For our project, we created a tool that allows users to compare the performance of various shortest path algorithms on a graph that represents the relationships between artists from Spotify. We used the Spotify API to collect data on artists, and we created a graph with about 18,000 nodes representing different artists and 120,000 edges representing connections between them. Spotify considers two artists related if a large number of the people that listen to artist A also listen to artist B. So for example, if a large number of people who listen to the Beatles also listen to John Lennon, they're related to each other, and so the shortest path between them is a single edge connecting them. We implemented three shortest path algorithms. So you can see here, if we want to find the shortest path between the Beatles and Guns N' Roses, we can use the first algorithm here, and it'll find the shortest path between them. So from the Beatles to John Lennon to David Bowie to Queen to Aerosmith to Guns N' Roses is the shortest path that connects the two artists. And you can see here how long it took to find that path for the first algorithm. And you can see if we run the second algorithm, it took slightly longer to find the path this time, but it found the same path. And finally, the third algorithm we implemented here, Dijkstra's algorithm, took a little bit longer than the first two to find the path, but it found the same path that connects the Beatles to Guns N' Roses in the same distance. The reason that Dijkstra's algorithm runs slower than the other two algorithms we implemented here is because our implementation of Dijkstra's algorithm doesn't make use of a priority queue, and because of that it runs much slower than it could. It's interesting to note that sometimes the algorithms will find different shortest paths, so they'll find paths of the same length, but the paths from one artist to another will be different. So for example, if we traverse from the Beatles to Ruby Rose, the shortest path that the breadth first search algorithm found is from the Beatles to John Lennon to Yoko Ono to Laurie Anderson, etc. But the Bellman-Ford algorithm finds a different path from Yoko Ono to Patti Smith, and then the rest of the path is different. But the paths are the same length, so they're both still valid shortest paths. You can also click on an artist to reveal the artist related to them. So for example, if I click on John Lennon, it will reveal all the artists related to John Lennon. And from there I can click on other artists, for example, Ringo Starr, and it'll add Ringo Starr's related artists to the graph. And you can do this for any artist as long as they have related artists stored. So for example, if I click on Guns N' Roses, you can see the artist related to Guns N' Roses, and click on Aerosmith, you can see the artist related to Aerosmith. And you can see in between them are the artists that are related to each, and then on the sides are the artists related to only one of those two. And you can zoom out and scroll and pan, view the graph. You can extend it into a larger graph, and it's actually pretty interesting to look at the larger graphs when you reveal a lot of related artists. Their behavior is interesting. Finally, off to the left here, we have some links with more information about the algorithms that we implemented, as well as a longer description of how we gathered our data.